Okay, good afternoon. Good morning, everyone. So previously I told you guys to watch video chapter 10, part 1 and part 2. Part 1 was about sound wave property, sound intensity, and also sound level. Then part 2 was on the Doppler effect. We're gonna do a little recap. Siapa yang belum tengok tu, saya buat benda ni laju-laju je. Recap macam biasalah. Recap is always fast. So siapa yang nak tengok in detail, please go back to the videos. If you have not, if you have, thank you for watching my video. Hopefully it will help you to better understand today. Okay, so kita nak buat new slide. Kita akan buat recap. Oh, wait. And no, stop. What's going on? Delete. Okay. So chapter 10 ni ada 4 subtopic: sound wave property, sound intensity, sound level, Doppler effects, and new waves. Now, sound is a type of wave. We've discovered that wave are the longitudinal and also transverse, right? We have transverse and longitudinal. Sound is a type of longitudinal wave. If you still remember, the displacement is right, left. So it's not really up and down. It's high intensity, low intensity, and then that high intensity will become your peak in the sine wave, and the low intensity part will become your trough, the dip, right? We've discovered that in chapter 9. So this is like an extension of chapter 9, but sound wave. So I wanted to talk to you guys about, so sound has different properties ataupun different speed in different types of media. For example, you know that in solid, sound travels faster, and in liquid, sound travels faster. In solid, sound travels faster than in liquid, and in liquid, sound travels faster than in air. So maksudnya yang paling slow sekarang ni either air or vacuum. So the more particles you have in the medium, the faster your sound wave can propagate ataupun your sound wave can travel. Propagate is another word for travel. Now, this is not the one that we're going to focus on, but this one, this equation. So speed of sound is also dependent on the temperature of the medium. So if the air that you are in, this is the air, udara, if the air that you are in has different temperatures compared to the other room, so the sound will travel at different speed compared to, depending on the temperature lah. Okay, so this is the equation. This is the one that we're going to focus on. There are two types. There are two properties that I told you just now. Speed depends. The speed of sound. Sorry, I'm stuttering. The speed of sound depends on the medium that it is propagating in, either solid, liquid, or air. And also the temperature of the medium also influences the speed. We are going to focus on the speed depending on the temperature. So this is the equation. So V equals to 331 square root of temperature over 273. Now the temperature here must be in Kelvin. Must be in Kelvin. So let's say your temperature in your room, you're in aircon, is 25 degrees Celsius. You have to convert that into Kelvin for you to know what is the speed of your sound. So 25 plus 273, you would get 298K over 273 square root and then times with 331, sorry. Okay, so 331, what is this value? This value is the speed of sound in air at 0 degrees Celsius. So this is like your reference lah. Typically, you would label this as V0 ataupun V0, the velocity or the speed of sound at 0 degrees Celsius. Okay, so the speed of sound I told you just now, it depends on the medium. The speed depends on the medium and also the temperature. So here, this is an example. In air, it is 331, and I told you in solid, it should be faster. So this is lead, it is a type of solid, it is 1322. So lajulah. Okay, and then I'm not going to touch this one. Kita nak recap je. So this is the range of sound yang kita belajar. The first one is infrasound. Infrasound is anything that is below 20 hertz, and then acoustic is the one that we can hear. So it's 20 to 20 kilohertz. I think you have seen this range, 20 to 20 kilohertz is the range that you can hear. And then above 20 kilohertz is called ultrasound. Ultrasound sangat high pitch lah. High pitch like the sound of the bat. Sometimes you can hear it, sometimes your ear can hear it, sometimes you can't. But the most comfortable range that we can hear is 20 to 20 kilohertz. below that and also above that, selalunya our ears are not designed to hear those frequencies lah. Okay. So this is infra, maksud dia kecil. Ultra maksud dia besar. Macam ultra marathon, ultrasonic, those means huge. Infra means small. Okay, this one we talked about. Application, boleh baca sendiri. So this one I already touched in class. Please refer to that video. Okay, so threshold of hearing. This is very important. Threshold of hearing is about 1 times 10 to the minus 12 watt per meter squared. Watt as in power, watt. And then per meter squared is area. Okay, and then the threshold of pain is about 1 watt per meter squared. So this, as low as this much intensity, you can hear it, but it is like barely, you can barely hear it. Sometimes orang tua, old people that their hearing has degraded, they can't hear this 1 times 10 to the minus 12. They have to listen to like higher intensity. So dia cakap, dia orang kena cakap kuat-kuat kan. This is because their hearing has degraded and the intensity, the threshold of hearing has increased. Maksudnya they can only hear like maybe, I don't know, 10 times 10 to the minus 12, contoh. So this is the amount of intensity yang diorang boleh hear. So below that, diorang tak boleh dengar. So kalau cakap perlahan-lahan, diorang tak dengar. Itulah. Okay, so this is the threshold of pain. This is like the loudest that you can hear before it starts to become painful. For example, airplane. Airplane bila dia nak start engine tu sangat bising kan. You feel like you're almost like it's almost painful, but not really, but it's kind of painful. So that's your threshold of pain. Almost there, but not really. So threshold, panggil threshold macam sempadan sebelum dia sakit. Macam itulah maksud dia. So 1 watt per meter squared. Okay, and then we have intensity. I told you there was threshold of hearing, 1 times 10 to the minus 12, and also threshold of pain, 1 watt per meter squared. And then intensity, which was 1 times 10 to the minus 12. Dekat sini, threshold of hearing, and also we have threshold of pain, 1 times 10 to the minus 12, and then this is 1. Dua-dua unit dia meter, watt per meter squared. So this is the equation. Allah. This is the equation for intensity. So this is change in energy over the change in time, or they say that at which the energy flows through a surface. Sorry, the rate at which energy flows. The rate maksudnya over time, energy is E through a surface. So bahagi dengan A juga. So energy over area over time. So 1 over area times change in E over change in time. So you know that change in E over the change in time is simply power. So basically intensity is power over time. Sorry, power over area. This becomes I equals to P over A. P is watt, area is in meter squared. Okay. So this is intensity. So this is the SI unit, watt per meter squared. So we talked about intensity. There's another term called sound level. This is sound intensity. The next one is sound level. Yeah, right? Okay. Oh, kecil ni slide saya sekejap. Sorry. Okay, so intensity of a point source. Oh, kita tak masuk lagi sound level. So intensity of a point source is I equals to P average over A. We talked about this just now. P over A ataupun P average over A. Typically, kita akan pakai P average lah. So sound travels in the form of spherical balls. Spherical balls. So if you have a radio, the sound waves, you feel like it travels like this. But if it is suspended in air, so this is the ground, this is you. You hang this radio, I don't know why, but you just feel like hanging it on the ceiling. This is your radio ataupun a speaker, portable speaker. The sound waves will travel like this. It will travel like this. So if you put it on the ground, it would travel like this. Sebab bawah ni nak travel mana kan? Orang dalam tanah lah dengar kan, tapi siapa dalam tanah kan? That is a scary question. So you have to remember that sound travels like a sphere. Okay, sphere. So it travels uniformly in a sphere. So at this point where this is R1, this is R1, this is R1, anyone within R1 will hear the same intensity. And if I'm over here and Daniel is over here, nampak macam jauh kan? Tapi we will hear the same intensity because we are within the same radius from the source of the sound. So anyone that has the same radius from the source of the sound will hear the same intensity because sound waves travel in spheres. And the sphere is 4 pi r squared. This is the surface area of a sphere. Rupa dia macam ni lah. Okay, so this is your equation that you have to remember, wajib. So I equals to P over 4 pi r squared. So let's say, saya nak panggil nama siapa hari ni? Dah lama tak panggil nama orang. Tadi dah panggil Daniel, let's call Sharifah and Wasilah. Okay, so Sharifah and Wasilah are best friends. I don't really know if you guys are, but let's say you guys are best friends. And so you wanted to hear the same sound. You want to hear the same sound. I don't know what sound that is. Maybe it's me. I'm the source. So this is me. I'm the source. And Sharifah is here. Sharifah is R1 from the source. And Wasilah is over here. You guys are both listening to my lecture. Pasal nggak saya baru buat example ni kan? Sebab macam mengarut gila. So R1 and then Wasilah has R2. So I want to know what is the intensity that Sharifah is hearing versus Wasilah. Okay, I am the source. I'm talking in class and Sharifah is over here. Wasilah is behind me. They both have different radiuses from me, which is the source of the sound. So I want to know what is Sharifah hearing, and I will call Sharifah punya hearing as intensity 1. And I will call intensity that Wasilah is hearing as intensity 2. So remember, I am the source here. They are both hearing the same source. So when you have the same source and you want to know the difference in intensity depending on the distance, you can use this ratio. So it starts from this equation first. So kita start dengan Sharifah dulu. So Sharifah is I1. So I1 P power of that source of sound over the area yang sound to propagate lah. So Sharifah is R1 from the sound source. So this means that the area through which the power of that sound travels is 4 pi R1 squared. This is the equation. 4 pi R1 squared. This is for Sharifah. Ini adalah intensity yang Sharifah dengar. P adalah sama untuk Wasilah dan juga Sharifah sebab they are hearing the same source. Ini adalah P source. So selalunya orang tak label P source lah. They label it as just P. Okay, now we go to Wasilah pula. So I2. Remember the P is the same, but the area ataupun the radius Wasilah is different than Sharifah. So 4 pi, 4 pi R2 squared. Okay, so now I want to know, okay, what's the ratio of this intensity? So I can equate them together with this P. Sebab P ni je yang sama. I akan lain, 4 pi R squared pun akan lain because they have the different radiuses. So I equate this P. So this Sharifah is I1 4 pi R1 squared and Wasilah is I2 4 pi R2 squared. I want to know what is the ratio between these intensity. So I just rearrange this. So I want to know the ratio of Sharifah versus Wasilah. So this becomes 4 pi R2 squared over 4 pi R1 squared. And then you can cancel that out. So this ratio becomes I1 over I2, R2 squared over R1 squared. Square tu kena ada, dia tak hilang. So please remember that. Do not put I1 equals I1 over I2, R2 over R1 sahaja. You have to have that square. It will become wrong if you don't have that square because We are talking about area, 4 pi r squared. Okay, so that is how you use that ratio, intensity from a point source. So you can identify you can calculate what is Wasila's intensity if you know what is the intensity of Sharifah. Intensity Sharifah dengar. So let's say Sharifah hears the threshold of pain. Kuat sangat. Sekejap, sabar. Kita fikir. Sharifah is hearing, let's say I1 is 1 times 10 to the minus 6. Okay, contoh Sharifah is hearing this much. The unit is watt per meter squared. Okay, so now I want to know what is Wasila hearing. Let's say R1 is 10 meter and R2 is 20 meter. Contoh. Okay. Okay, so now I want to use the ratio. Let's use this ratio. Kita boleh padam semua. Kita nak tahu berapa intensity yang Wasila dengar. This isn't like a recap, tapi tak apalah. Okay, so I1 is 1 times 10 to the minus 6. I'm using this equation, this ratio. 1 times 10 to the minus 6. I don't know what intensity Wasila is hearing, so this is what I'm trying to find. And R2 is the distance of Wasila, which is 20 meter. 20 meters squared, and the distance R1, Sharifah from the point source is 10 squared. So whatever this value gives you, I2 is watt per meter squared, and this is the intensity that Wasila is hearing. Adakah lagi kuat ataupun lagi rendah? Is it going to be louder or fainter? What's your guess?
Slower.
It should be smaller. If you are far away from the source, you are further away from the source, you should be hearing something smaller ataupun fainter. If you are closer, you would hear something louder. So if you are using this ratio and you discover that Wasila's intensity is greater than Sharifah, you know you're doing something wrong. So please check back your answer. Okay? So always use your logic bila dah dapat jawapan tu. So that is intensity. Intensity is power over area. What area are we talking about? Which is the sphere, 4 pi r squared. You can also use this equation to make your ratio. If you know the intensity of one person, so you can know the other one, provided that you know the distance of them both from the source. They have to hear the same source for you to use the ratio. Now we're talking about sound level. So sound level is called beta. You don't have to call it beta, you can just call it sound level. So sound level is equal to 10 logarithmic. Let me just call it log. 10 log I over I naught. So what is I naught? I naught is the threshold of hearing, the smallest intensity that you can hear. Not the threshold of pain. The smallest intensity that you can hear, which is 1 times 10 to the minus 12. Ini adalah equation dia. Wajib pakai this number. This is the constant that you have to use. So when they tell you, okay, what is the threshold of human hearing? What is the sound level of human hearing? So you put in the threshold of human hearing, 1 times 10 to the minus 12 in your I, and your I naught is basically the same thing. So the threshold of human hearing in terms of sound level is actually 0 dB. So if they tell you the loudness of this speaker is 0 dB, you know that it gives you the faintest sound possible for our hearing. So that is 0 dB. And if the loudest sound level that we can hear is before it becomes painful is actually 120 dB, which is the threshold of pain. Kita tahu threshold of pain is 1 times 10, it is 1 watt per meter squared. So you just put that into your equation over your threshold of hearing. So use your calculator, you would get this as 120 dB ataupun decibels. Okay. So kena tahulah mathematically you have to know how to do this. And if they give you sound level, macam mana nak convert jadi intensity. If they give you intensity, macam mana nak convert jadi sound level. So those are possible questions that they can ask you in the exam. Betul saya cakap betul-betul ni. There's a possibility that they ask you how to convert sound level to intensity, intensity to sound level. So sorry for my voice. It's not very clear today. Okay, next one. Kita in my video, we also talked about how to convert this. You can go back to that video for exercises. We already did this one. And then I talked about Doppler effect. Doppler effect. What is Doppler effect? Doppler effect is that phenomenon whereby the further you are from the sound source, the slower the frequency. Contohnya macam ambulance, they sound macam mana sound ambulance? Nino, 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 macam tu kan. So the closer you are, okay, let me draw a diagram. This is you, this is the ambulance. Kenapa ambulance lupa macam ni? Tak apalah. So the ambulance is approaching you. You are not the victim, you are just a passerby. Inshallah. So this is the ambulance, is moving towards you. So the sound is nino, nino, nino. But as the ambulance goes closer to you, it goes nino, 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 nino. As it goes further, as it goes closer to you, the frequency ataupun the beating of that nino, nino, nino tu lagi laju. It becomes mula-mula nino, 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 and then nino, 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 nino. Macam jadi annoying dah lah kan. So this is called the Doppler effect. And then doesn't stop there. And as it passes you, it goes away from you, right? So this is your ambulance. This is not your ambulance. This is the ambulance. It is now moving past you and goes further away. So tadi nino, 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 and then sampai tak dengar. So that is called the Doppler effect. It's a phenomenon whereby the closer that source is to you, the higher the frequency that you hear. The further away that sound source is to you, the slower the frequency of that sound source. And so that this phenomenon is described by this equation, F naught over Fs equals to V plus V naught over V minus Vs. Now, F naught, this naught is not naught, it is actually O. Should I call it F naught or FO? FO lah kot. Okay, tapi dia label as 0. It should be labeled as O. So this is FO over Fs. FO is the frequency heard by the observer, and Fs is the frequency heard, the frequency of the source, sound source. This is source. The observer is you. Let me write that as observer. So this is equation, this is your general formula. So this is V plus V naught, and then V minus Vs. So this is the velocity of the observer. If you are static, then put as 0. Static meaning you're not moving, you put it as 0. If you are moving, then we will talk about that. And then this is the speed of the sound source. If the sound source is not moving, you put it as 0. If it is moving, we will talk about that. So the air, we are assuming the air is stationary. Use positive values when observer and source approaches. Okay, for example, this is you, and we have an ambulance. Let me draw this somewhere else. Tadi saya pergi Hianxi. By the way, this is a cafe next to the main library in UPM. Nanti next semester, if you are going to come to Asasi, inshallah, hopefully, God willing. So if you want to meet me, we can meet at that cafe. It's quite near to Asasi. So next semester is semester 2, right? I won't be teaching you guys anymore, but you can still meet me. Okay, so this is the ambulance. This ambulance is approaching you. This is your source sound. Source of sound, kan? And you are the observer. I'm so sorry kalau orang dah tengok and dia dah faham semua. Saya ulang balik untuk orang yang tak faham. Okay, sound source sebab saya suruh tengok video je kan. So source of sound, and this is observer. So the source of sound, in this case, it is moving with some velocity. So we're going to call this as Vs. And you are not moving, we're going to call you as VO ataupun V naught. And you are not moving, so you are zero velocity. Now let's use this equation. This ambulance is approaching you. You by right, you will be hearing frequency of the observer, the frequency heard by the observer will be higher. frequency heard by the observer should be higher. This is our hypothesis. Let's see if this equation fulfills this hypothesis. Okay, so F naught is what we're trying to find. Fs sound source patutnya diorang akan bagilah. So assuming that we don't know, kejap. V plus V naught, this is 0. And then V minus V source, let's say it is moving towards you. Laju lah kan, ambulance selalu laju 60 km per hour. Tak laju sangat lah, okay je. So you have to convert this to meter per second dulu before you can use it into this equation. So let's say, saya malas nak kira. Let's say this is berapa lah? 70 meter per second contoh. So we're going to put this as, sabar jap. So use negative values when observer and source is moving away. Use positive values when observer and source approaches. So in this case, you are not moving, but the source is moving. Approaches. So you have to use positive value. So let's say you have 70 meter per second. So you put in positive 70 meter per second. So this is how you use this equation. Let's say the ambulance is moving this way. It is moving away from you, but the velocity is still the same. So this is moving towards. Okay, and then this is moving away. Okay. Nanti kita buat betul-betul sabar dulu. Saya ajar pakai value dulu. So FO over Fs equals to V plus 0, you are not moving. This is the velocity of the observer. Excuse me. Okay, and then V, it is moving away. So you have to use negative value, kan? Okay, so negative value minus 70 meter per second. So what does your equation become? Okay, so this is moving towards, this is moving away. So now, what is V? V is the velocity of sound in air. This is a constant value. V in this case is always 331 meter per second. Always, It is the same value as this guy. Let me show you guys. Mana dia? Jauhnya. Okay, this one. Speed in air. So we are going to use this value 331 ni for all cases of Doppler. Kita akan assume semua temperature constant and the air is not moving. The air is having this constant speed lah. This is our assumption to simplify the problem. Okay, so our assumption is V is 331. So now I substitute that. Kenapa tadi tulis? Hello, what's going on? I think there's a loose connection. Is it? No. What's going on? Kejap. Stop sharing. Save as. Does anyone have any questions for the time being? Everyone okay so far? Mesti takut nak tanya sebab tak tengok video lagi kan? Tak apalah. Jadi bila sempat dia tengok. I know you guys have like a lot to catch up. Sekejap Terima kasih. Namanya. Okay. Lamanya. Sekejap Okay, tutup. No questions So everyone's okay so far? That's good. Silap. Oh my god, no. Cancel.
Okay.
Oh, for the time being, saya nak cerita pasal quiz lah. So your quiz is on chapter 11 and chapter 12 kan? And you guys have received the schedule yet for the quiz for all subjects? Dah ke belum?
Yeah.
Dah kan? Okay.
Yes.
So
Yeah.
physics is on Wednesday, right? If I'm not mistaken. But the quiz is supposed to be 1 hour, right? And it is on chapter 11 and chapter 12. However, because sebab saya cakap ni, sebab unit fizik ni baik, puji diri sendiri kan. So sebab unit fizik ni baik, but I'm telling you this seriously, sebab kita orang first sebab tak habis belajar lagi kan, and second sebab unit fizik ni semua macam baik hati. They are giving you guys 1 week to complete, not 1 week lah, 5 days to complete the quiz. 5 days 5 days instead of 1 hour. So at chapter 11 and 12, kita akan sambil quiz tu akan open on Monday 12 AM and it will end on, if I'm not mistaken, Friday lah 11:59. If it's not Friday, it's going to be Sunday, either Friday or Sunday. Saya tak ingat, saya akan confirm balik. So 7 days or 5 days, saya tak ingat. And during that time, the quiz is open, meaning to say it is available on website for you guys to do. Do not copy each other. You guys will have different questions anyway, tak boleh copy pun. Kita akan sambil quiz tu sambil kita belajar lah. So I will try my best to touch on the things that the quiz tanya lah. Okay, but I won't do it so directly. I will try my best to cover the things that the quiz is asking. So kita tak akan cover all chapter 11 and all of chapter 12 because it's a lot. So I will touch on, I will teach you guys on things that the quiz asks lah. Okay? So that is how it's going to be. Sebab this is week 17 and kita baru nak habiskan chapter 10. So next class is chapter 11. And then you guys have 1 week of quizzes. So I don't think the learning is going to be very conducive because you guys are having quiz. So that is how it's going to be lah. Okay? So don't tell this to other lecturers, please. Only unit physics yang tahu. If this gets out, this info where we are giving you 1 week instead of 1 hour gets out to the admin, to other lecturers punya subject, we will be in trouble lah. Okay, so please keep it between us. This is unit physics punya secret to help you guys. Okay, sebab final akan confirm susah. So quiz is when we want to help you. Okay, so do your best for the quiz and also do your best for the finals. But remember, we are not here to penalize you. We are here to help you learn. So try your best. Sometimes you get it, sometimes you don't, but try your best. And whatever result that you get, it is always good enough if you did your best. Okay. So that's it from me lah. Okay, so that is about quiz. So let's continue. Secret tau, jangan beritahu siapa. Kejap. Let me share the screen. Alamak, this is recorded. Tak apalah. Kenapa tak boleh share lagi ni? Nampak tak slide? Ke tak? Nampak kot.
Nampak.
So sebenarnya like the planning for this semester is quite like haywire sebab banyak kali kan tukar jadual sebab MCO, sebab I mean like all the variants lah, and then spike in cases. So kesian lah korang sebenarnya, but it's okay, we try our best. Okay, so this is why the planning for the semester is like macam meripik sikit. Semua rapat-rapat. Mana tadi? Let me go back. Okay, so this is what we talked about. Remember, if you are approaching ataupun the sound source is approaching, always use positive values dalam general formula. If you are moving away, you are like pergi ke kiri and then ambulance pergi ke kanan, dua-dua pakai negative values. Okay, so in this case, we are talking about when you are stationary and the ambulance is moving towards you or moving away. Let me use my pen. So moving towards is in blue. So let's use this in blue. Lemak. Tak apalah, blue This is moving towards. Moving towards in blue and moving away in pink. So this is going to be positive 70 and moving away is in pink and that is minus 70. You are static, that's why this is 0. And then we also talked about the value for V. The value for V is constant. It is always going to be 331 meter per second. Sometimes they give it to you, sometimes they don't. Just remember the V that you should use here is 331. Sepatutnya diorang bagilah 331. So put that in this equation. 331, 331, 331. And then if they give you the frequency of the source, you put this inside. If not, you will find out the ratio of FO over Fs from this equation. Apa lagi saya nak cerita? Okay, what if both of you as the observer moving away and the ambulance is also moving away. So moving towards, in this case, tadi kita cakap ni moving towards, source is moving towards, but observer is static. Is not moving. Kan? Moving away, source is moving away and observer is static. So now we're talking about what happens when both of you are moving away or both of you, seorang approaching, seorang moving away. How does that work? How does the equation change? Sama juga. I want space. Let's use a different slide terus. Okay, I'm going to copy this. Okay, I'm going to copy this. This is your general formula. And then kita akan pakai positive values if approaching. And then minus values if moving away. Okay, so kita akan buat jadual. Kita akan buat jadual untuk different cases. Four columns. If anyone has any question, please stop me. Stop. So Doppler ni sangat famous Doppler punya problem for exam. So make sure you know how to use the equation. Okay, so I want to know what is my Vs, speed of source, V of the observer, F of sound if they give it to you, and of course F observer is what we're trying to find. Sometimes they give you F observer, they want you to find F source, vice versa lah. So semua ni diorang boleh tanya. Okay, if they give you this guy, and this guy, they will ask you what is Vs and so on. If they give you Vs, Vo, Vfs, they will ask you Fo, stuff like that lah. So these are the 4 parameters. Why am I using orange? It doesn't really show up. Let me use Fo, Fs, Vo, Vs. Terbalik pula, tak apalah. This is our general equation. Okay. So let's say I need another column. Kalau recap kan macam terlebih detail je, tak apalah. Okay. Kecilkan. FO, FS, VO, VS. We have several cases. One where the source is not moving. Okay, source is not moving and observer is moving. So kalau moving, saya akan cakap M. Kalau static, meaning to say it's not moving, I will say S. So kita akan short formkan dia kat sini. So O, observer, I'm going to call observer as OB. OB is moving. Source, I'm going to call this as OSO dot is moving. Okay, moving towards. Saya cakap, how do I make this? Kita start dengan tak bergerak dulu. Source is static. Moving towards. Moving towards. T. Moving away. A. Okay, so M moving towards MT. Source is static. Observer is moving away. Source is static. And then we have observer moving away. Source is moving. Kita buat observer kosong dulu. Observer is static. Source is moving towards. Okay, observer static. Source is moving towards. Panasnya. Moving towards. Okay, and then we have observer static. Source is moving away. Okay, and then we have observer moving away, but source is moving towards. And then tak cukup lagi satu, bawah ni, observer is moving away, source is moving away. Ada tak dulu? Tak ada. And then moving towards, alah banyaknya. Ada banyak case How do I do this? We need more columns. Moving away, moving away, moving towards, moving towards, moving away, moving towards, moving away, moving towards, moving away. So nak lagi 4. 1, 2, 3, 4, 5, 6, 5 plus 10 je lah. Sekejap I want you guys to know how to use this. Ini adalah kerja sia-sia. Kena saya tulis. Okay, then padam ni. It's kind of hot. No questions so far? So everyone's doing okay? This is 8, 4, 5. Okay, and then I'm going to add another column. Insert. Rows below. Okay. So why am I doing this, going through this length of like making this table? Because when I was learning this, I wish my lecturer did this. So this is what I'm doing for you. Because I didn't understand what was the Doppler effect. Okay. Kalau tak faham, tolong tanya. Tolong tanya. Jangan tak tanya. This is the time. So FO, FS, VO, VS. This is the frequency of the heard by the observer. This is the frequency of the sound. Ini heard. Frequency yang didengar oleh observer. You are the observer. You are not emitting sound. We are assuming you're not talking. But the sound of the source is FS lah. This is the source punya frequency. This is the velocity of the observer, meaning to say whether you are moving or you are not moving. And this is the velocity of the source, whether the source, like the ambulance, is moving or not moving. If you are talking about a radio does not move. So the radio is static. So sometimes it moves, sometimes the source does not move. And then we have cases here. We have cases whereby the observer is moving away, source is static, source is SO. Then we have observer is moving away, moving towards, source is static. So moving away, moving towards. Then we have observer is static, source is moving away. Observer is static, you are not moving. Source is moving towards. And what if both of them are moving? You are moving, ambulance is also moving. It becomes a little bit complicated, but we can solve it using the equation. Observer is moving away, source is also moving away. What if you are moving towards, but source is also moving towards? And then you have observer moving away, and then source is moving towards, and then you have observer moving towards the source, but the source does not like you, so it is moving away. So these are the cases. We have 1, 2, 3, 4, 5, 6, 7, 8. Oh, 8 je. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7, 8. Saya kira macam 10 tadi. MAT. Okay, betul. Okay, so now we talk about the V for this guy is always going to be 331. So we are not concerned about that value. So the frequency of the observer, we're going to talk about the V lah kat sini. So V, this is the result. So V is what we're going to discuss here. So V of the observer, if it is moving away, it is going to have a negative value. If it is moving towards, it is going to have a positive value, Vs. So this is the sound source. It is static, 0, 0. Observer is static, 0. Observer is static, 0. Sound source is moving away, negative value. Sound source is moving towards, positive value. And then this is moving away, negative. Moving away, negative. Moving towards, positive. Moving towards, positive. And then observer is moving away, negative. Moving towards, positive. Moving towards is positive. Away, jauhan, negative. Excuse me. Did I cover all cases? I think so. Okay, so now kita tengok with this positive, negative semua ni, kita akan assume V not VO, if it has some value, is going to be 70. V source is going to be 50 if it is moving. So that's now kita tengok how to put into this equation. Where should I put my legend away? Korang faham lah kot. Okay, so now kita tengok logic tak when we put this into the equation. So let's say observer is moving away, source is static, right? Kita dah cakap pasal ni, observer, so F naught Fs, so this is going to be 331 plus V moving away minus 70 over V minus ni kena kekalkan, so positif atas, negatif bawah. Tapi disebabkan dia moving away, observer is moving away, it is negative. And then your source is static, so this is going to be 0. So now if you try to solve this, you would find out that 331 minus 70 is 2 something, 200 plus. And V is 331, right? So your FO over Fs, this is FO is smaller than your Fs. The frequency sound is higher, FO is smaller. The frequency heard by the observer is going to be less than the actual frequency of the source. So, kenapa? Because it is moving away. Kita cakap pasal moving away tadi kan? So, if you are moving away, bayangkan ambulance tu tengah bergerak jauh, menjauhi korang. So, it becomes Nino, 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 sampai dia berhenti. So the frequency heard by you guys is actually smaller than the actual frequency of the ambulance. So orang dalam ambulance tu yang dengar, dia dengar Nino, 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 constant kan? But because the ambulance is moving away from you, the frequency is Nino, Nino, Nino. It's very slow instead of the actual frequency. So this is the actual speed. The speed that you are hearing is smaller. This is why the ratio of FO over Fs is smaller. 200 over 331. My calculator. Alah, this is calculator museum. Saya tak. Mana tak calculator yang satu tu. We use my phone. So you know that 200/331 is basically less than 1, right? To logic lah. 200 divided by 331 will give you something 0.6. So if the ratio of FO/Fs is less than 1, in this case it's 0.6 something, you know that you are hearing something that is less. The frequency you are hearing is less than the actual frequency. And logically, this is correct because you are moving away from the sound source. The ambulance is static, sorry. You are running away from the ambulance. This is the ambulance. Ambulance is static. Bunyinya nino, 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 nino. Tapi you are jogging towards the other way. So what you're hearing is nino, nino, nino. Bunyi macam nak mampus. Ambulance tu, sorry. Bunyi macam nak hilang, kan? So that is what is going on. So this equation tells you how to do that. I mean, it gives you the exact frequency lah. Okay, so let's take another case. In this case, we have observer moving away, but the ambulance is moving towards you. So how is that? Padam jap. Okay, so macam mana rupa moving away tapi ambulance, you are jogging. Nak jogging juga kan sebab saya suka jogging. So this is siapa? This is Alia Adriana. So Alia loves to jog because she is a fit person. So this is Alia. So Alia tengah jogging to the right and an ambulance is approaching her. An ambulance is approaching her. Alia is not jogging very fast because dia manusia kan. So dia jogging maybe berapa 10 meter per second. No, that's too fast. 2 meter per second. Maybe, no, this is too fast. 0.5 lang per second. 0.5 logik tak? 1 lah, 1. Dia cakap Alia ni laju lah. Dia seorang atlet. So 1 meter per second. So Alia is jogging 1 meter per second. The ambulance is approaching 70 meter per second. The ambulance is approaching you, but Alia is at the same time, they're moving away. Okay? So how does that work? So FO/Fs equals to 331 plus Alia is moving away. So the moving away is observer moving away. This is her. Sorry, this is not the case. Moving away, SO is moving towards this one and this one. This is the case number 7. So Alia will have negative velocity, but the ambulance will have positive velocity. So -1 and the ambulance, dia laju kan? Ambulance laju 331 minus moving towards positive. So this is going to be positive 70 meter. Okay, let's see what is the ratio that is Alia is hearing. Is it going to be less than the frequency of the actual sound? Actual sound source, or is it going to be greater than the actual sound source? What do you guys think? Lagi besar frekuensi ke lagi rendah frekuensi daripada actual ambulance punya sound source? Actual ambulance punya frekuensi. Alia dengar lagi kuat ke lagi perlahan? Come on guys.
What?
Lagi kuat kot. Any other guesses? Kalau kuat, kenapa kuat?
Sebab the ratio more than 1.
But the ratio is more than 1. Okay, from this equation, betul. The ratio is more than 1. But logically, kalau kita try imagine pun, Alia moving 1 meter per second je. Dia gerak macam perlahan lah kan sebab dia manusia kan. But the ambulance is very fast. So kalau kita fikirkan pun, Alia akan dengar macam tu kan. Walaupun orang dalam ambulans tu tak dengar macam tu. Orang dalam ambulans dia dengar nino, 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 nino. Dia dengar constant je sebab dia dalam sound source. Tapi Alia yang kat luar ni, as observer, dia akan dengar mula-mula nino, 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 nino. Dia frekuensi dia lagi tinggi daripada actual frekuensi sebab it is moving. Kalau ambulans ni statik, dia akan dengar sama macam orang kat dalam ambulans lah. Nino, 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 nino. Macam biasa je. Tapi sebabkan dia bergerak, frekuensi tu jadi rapat. Dia jadi rapat lah. Dia jadi rapat. So this is why Alia is hearing frekuensi yang macam betul ke daripada ambulans. Tapi betul because the ambulance is moving. So here, when we put in the values, you would see that it is 330 over minus 200 something. So the ratio is greater than 1. When the ratio is greater than 1, Alia will hear something that is like crazy punya frequency. Laju lah. Bunyi yang sangat beating dia macam tu. Kalau versus Alia and the embrace moving away, bunyi dia the frequency is far apart. Okay, the beating is far apart. So use this table. You don't have to memorize this table. You just have to know if you are moving away, positive ke negative. If you are static, it is 0. V is equal to 331. You have to know there are different types of cases and you should put in the magnitude ataupun the signs accordingly. Jangan fikir mula-mula put in the values and then fikir logik ke tak logik your substitution tu. Okay, we're going to move on from Doppler. We're going to continue with standing waves after this. So let's take a 5-minute break. Let's continue at 11:55. Kalau soalan boleh tanya. Hi everyone, are you guys back? Ada soalan tak? No questions? There's no in my chat as well. I'm going to assume tak ada soalan lah. Okay, so the next subtopic is called standing waves. Am I still recording? Yes. So it's called standing waves. Yep. So now, ubat sesama. Bukan, ubat tekak. Okay, so imagine that you have a string, right? And, bukan. Korang pernah tak main like this toy whereby you stretch it and then when you stretch it, it becomes like this. Tak tahu lah korang sempat main ke tak benda tu. So dia ada macam dua benda ni. And then this is your hand. 3 jari je. When you stretch it, it becomes like this. Lepas tu dia bunyi zing macam tu. Ada tali kat tengah-tengah tu. When you stretch it, dia make like a pattern. Pernah tengok tak benda tu? I don't know what it's called. But similar to that, this is an application of standing wave lah. Dan kan waktu kecil-kecil lagi dah belajar pasal physics kan. So this is one application, and another one is when this machine is vibrating a string, this string is actually vibrating up and down, but what you see, your naked eye, what you see is bentuk macam ni. What you're seeing is this. This is what you're seeing, but in reality sebenarnya this string is moving up and down, but you can't see that because it's too fast. And so this is what you're seeing lah, nampak bentuk mata tu je. Okay, let's see if we can find an example on the internet. Standing wave toy. Oh, ada. Sekejap, kita tengok demo dia. Macam menarik je. Chrome, share. Standing wave demo.
Okay, for this demonstration, I have my able assistant, Parker. Parker, smile at your admiring audience. And we will be demonstrating transverse standing waves.
Can you guys hear the
I'll also
audio?
demonstrate traveling.
Yes.
Here's a traveling wave. I'm starting the wave by creating a disturbance here with my hand that is perpendicular to the direction of propagation of the wave. So I'll move my hand up and down.
So what is that? It's a transverse wave.
The little bump in the
and
spring
wave is caused by the
travels
disturbance.
from me to Parker and then back to me again. And you notice that when the wave hits Parker's hands, because he's holding it firmly, what was a peak heading toward him converts itself into a valley as it bounces off of his hands. So then a standing wave is where you pick a frequency that matches the length of the string in such a way that the waves created from my side of the string and bouncing off of Parker's coincide with each other and reinforce each other to create a standing wave pattern. The lowest frequency standing wave pattern is this one. It's called mode, M-O-D-E 1.
Okay, this is dia pilih a frequency. Let me try to recap this. They pick a frequency that matches the length of the wave. Matches the length of the string. And in this case, this is the first fundamental wave, fundamental mode. Jadi kita akan belajar apa fundamental wave ni. It is basically half a wavelength. So wavelength kan bentuk dia macam sine kan, macam ni. This is one wavelength, right? A sine. But in this case, it's only half a sine wavelength. So this is half wavelength. And it is called the fundamental mode. So this is number 1 standing mode.
Or the first harmonic.
First harmonic or fundamental
words,
mode.
Also called the fundamental mode. It's the lowest frequency mode.
So, can you go out? It's too loud.
That you can get in a transverse standing wave. If I double the frequency of that mode, I get the second harmonic or second mode, and sometimes called the first overtone. And this one, if you'll notice.
Okay, so here, this thing is moving up and down, up and down, up and down. Tapi what you're seeing is like mata kan, macam nampak mata atas, sorry. How do I say this? You see this part moving. Sorry, you see this here, and also you're seeing this one and this one. You don't see like tengah-tengah ni tak nampak sangat kan, walaupun dia gerak atas bawah, tapi yang tengah-tengah ni tak nampak sangat. This is called the standing wave untuk second harmonics ataupun F2. Okay, tadi fundamental mode ataupun first harmonic. This is called the second harmonic ataupun F2, and it is one wavelength. Tadi separuh je. This is one wavelength. Okay, let's continue.
This is going twice as fast as the fundamental mode. It has a node. It's exactly halfway between Parker and me. And that's a node.
Okay, so the node is here. This is the part where tali tu tak bergerak. Nampak macam tak bergerak. So if you can see, this part and the downward part is moving. This part and this part, we know that they are moving up and down, up and down. But this part where it's not moving, it appears as if it's not moving, is called the node. Tempat yang bergerak ni panggil anti-node. Okay, saya cerita dulu nanti kita cerita balik semula.
Where there's approximately no motion going on. So now I'm going to try and triple the frequency and get a standing wave pattern that coincides with the third harmonic or second overtone. Try again.
Susah sebenarnya nak dapatkan standing wave ni. Okay.
Okay, I think I've got it approximately now.
Tak berapa cantik lah.
I think I had it for a little while there. That's the third mode, where the string vibrates in 3 separate segments. And there's actually an infinite number of these modes that you can get. And see if I can get one of the higher modes. I think that's 4.
Okay, stop. Alah, tak nampak.
And
susah nak
if
dapat.
you're really, really good, you get 5, 6, 7, 8.
Okay,
so.
let's stop. Boleh abaikan suara-suara tu ya. Okay, share screen. Okay, so what was that? So kita boleh imagine benda yang sama berlaku kat sini, where this is Parker, the dude with the ketat face, and this is the professor yang buat vibration tu dia buat vibration sekejap. Okay, come. Yeah. Out.
Oh, you far?
It's too loud. Okay, continuing. Sorry, macam banyak gila distraction ni. Okay, so imagine this vibrating blade as the professor and the wall as Parker. So Parker punya muka wall, sesuai lah dengan muka dia kan. So professor tu dia vibrate in a way that the frequency, dia pilih macam vibration in a way that it matches the length of the string. So macam mana nak match this, the length of the string? Let's talk about standing wave now. So this is called a standing wave. A standing wave is when you have like this movement of the maximum to the minimum amplitude in one segment, and you have one segment where it does not move at all. It completely is stationary. Tengok kat sini, dia stay je kat sini. And then you have another segment of this guy moving up and down. And if you have more frequency, sometimes they look like this. Dia akan bersambung-sambung lah depending on how many frequencies that you have. In this case, you have 1 and 2. So this is 2 second harmonics. Okay, so let's talk about that. So how is a standing wave formed? So it is basically when you are, you vibrate, you are channeling incident wave, right? We are channeling incident wave, kan channeling lah. You are making the incident wave travel, like the disturbance to travel to the right. This is the professor, dia tengah vibrate. So the wave moves to the right and ada wall. Wall tu parker lah. So the parker pula, the wall acts to reflect the wave. So dia akan reflect. So this is called incident wave. Kita dah belajar ni. And then we have the reflection of the wave. So when the incident and the reflection overlap, when they overlap together, we call this as superpositioning. Superpositioning means overlap lah. So when they overlap, they will either add together or they will cancel out each other. So let's see. Kalau kita cuba tengok kalau benda ni, bagi stop tak boleh bagi stop ke? Okay, let me draw lah. So you have instances where the reflection, this is the incident wave, and this is the reflected wave. So if my reflected wave is like this is my reflected wave, and when I add them together, we call this as the overlap of these two waves, incident and reflected. But we call this term officially panggil superpositioning. Sebab wave, bila kita tambah wave together, we call this as superposition. So tambah of these two waves is called superposition. So if you see this word, don't get confused. It's just basically addition. So when you have like a 10 over here, and this is like 0, because this we are assuming this is amplitude kan, and this is like minus 10, and then this is 10, this is 0, this is 0, and this is minus 10. Imagine our sine wave, kita label the amplitude, maximum amplitude, and also there's a part where it is 0 displacement, right? So this is the incident, and then we have our reflected wave. Our reflected wave pun sama, ada minus 10, ada 0, ada 10, ada 0, ada minus 10, and then when the 10 is added, when the 10 is added to the minus 10, they cancel out to become 0. When they are added together, they become 0, and this is the node. Node dekat sini. This is the node because they are cancelled out. Okay, kalau tengok kat sini, dia sama lah kat sini. This is the 10 minus dengan 10 ataupun 10 plus minus 10 becomes 0. This forms the node. And then you have over this guy, 0. This is a 0, but you have some value over here which is 10. So instead of the node, now you have something that is at 10. And then over here, you have minus 10. Tapi yang ni bukan minus 10. Yang ni apa tak tahu. 3 maybe. So maybe you have minus 10 plus 3 is minus 7. So maybe it's over here. So the addition of these two waves form this guy. It forms this guy to be up and down, up and down. Kenapa dia bergerak-gerak? Sebab benda ni dia tak statik. Dia bergerak ke kanan. Seorang lagi bergerak ke kiri. So pertambahan antara dua-dua benda yang bergerak ni of course akan menghasilkan sesuatu yang bergerak jugalah. But in this case, it is called standing wave, and dia gerak ke atas dan ke bawah sahaja. Okay, I'm going to repeat myself here. Perbezaan antara normal wave versus standing wave. Normal wave bergerak ke kanan ataupun bergerak ke kiri. And you have two types, transverse and also longitudinal. And when we talk about standing wave, it means that we are seeing the amplitude going up and down, but the node will remain the same. Kita takkan tahu dia bergerak ke kanan ke, bergerak ke kiri ke sebab dia standing. Dia nampak static tapi dia go up and down. That is called a standing wave. Berbeza dari wave biasa. Okay. So any questions about what is standing wave? Faham ke? Tadi pun ada demo dah. So that is standing wave. It is moving but you can't see it's moving. So the formation, the combination of these two moving waves gives you something that is a standing wave. Benda yang nampak static. Okay. So I told you the place where there's no displacement at all is called the node. This helps us to identify berapa segmen dalam satu string ni. So this is the first segment, this is the second segment, and kalau ada lagi third segment, and so on, fourth segments and so on. So the nodes from one node to the other, this is one segment, segment ni tak official lah. Let's not call it. From one node to the other, this is one eye, one node to the other, one eye, one node to the other, one eye. The place where it moves up and down is called the antinode. Terbalik kan, anti. Dia tak suka node. Node tu tak ada displacement. Antinode ni maximum fluctuation atau maximum amplitude up and down. So a node occurs where two traveling waves have the same magnitude of displacement, macam ni, 10 and then minus 10. They have the same magnitude but they cancel out sebab dua-dua amplitude seorang positif, seorang negatif. They are in opposite direction, so they become zero. This is node. The net displacement is zero at that point. The distance between two nodes is half a wavelength. Remember, one wavelength is this much. If it is only half, this much, from node to node, this is 1/2 lambda. This is one complete lambda, one wavelength. One complete cycle is 1 lambda, half cycle is half lambda. An antinode occurs where the standing wave vibrates at maximum amplitude, either up and down. Okay. So when a traveling wave reflects back onto itself, it creates a traveling wave in both directions. The wave, blah blah blah. We saw this. Seorang incident, seorang reflect. Bila combine akan jadi standing wave. Tapi dia tak boleh combine sesuka hati. They have to have a certain frequency. As you can see that the professor demonstrated, kadang-kadang jadi, kadang-kadang tak jadi. Sebab kadang-kadang tangan dia vibrate tak betul. Vibration tu sangat penting. The frequency at which the string vibrates is very crucial to give us the standing wave. At the wrong frequency, the standing wave will not form. It will just look like jumbled up waves. Okay. So this is the lowest frequency called the fundamental frequency or the fundamental mode. Fundamental mode ataupun the first harmonics. Now, one thing I forgot to mention to you guys, for this type of standing wave, we are assuming both ends are fixed. Both ends are fixed. Dua-dua fixed. So Prof ni and then Parker, dua-dua tak bergerak, dua-dua pegang, cengkam, cuma Professor ni give the vibration. But both ends are actually fixed. Kalau dia tak fixed, kita akan cakap kemudian lah. Okay. So both ends are fixed. The first frequency is called the fundamental mode or the fundamental frequency or the first harmonics. Fundamental means 1. So the speed of wave, we know this, V equals to F lambda. This is from chapter 9. And then for a string, V is equal to tension over mu. Mu is mass over length. Okay. So this is tension as in Newton lah. The tension in the string. We're talking about string. We want to know what is the tension in the string. And then we want to know what is the V, because V tells us the frequency. V equals to F lambda. So when we substitute V equals to F lambda into equation V equals to T over mu, square root T over mu, we get this new equation. Saya letak F lambda kat sini. Wait, dia tak buat macam tu. Dia rearrange. V is equal to dia buat F as the subject. So if F is the subject, it is V over lambda. And if V is this guy, so it becomes 1 over lambda square root T over mu. So this is the equation that we have. So F1 V over lambda 1 kan equals to 1 over 2L T square root T over mu. Now you're wondering mana datang 2L ni pula? We talked about lambda. Kenapa dia tiba jadi 2L? Okay. So in this case, we saw that the fundamental mode happens when it is half a wavelength. So imagine this is the length of the string. The length of the string is called L, and L is equal to half the wavelength lah, ataupun half cycle. So L is equal to 1 over 2 lambda. So if I want to substitute lambda in terms of L, so I need to, lambda is equal to L. Okay, lambda is equal to 2L. So I've substituted lambda as 2L over here. So I would get F1 equals to V over lambda 1 equals to 1 over 2L. 2L is the lambda, this guy over here, square root T over mu. So this is the equation for your fundamental mode. Tak perlu derive, I'm just telling you how to derive it. You just have to memorize this equation. So F1 equals to V over lambda 1 equals to 1 over 2L square root T over mu. And again, when we see this type of shape, it is called the fundamental mode. It is half a wavelength. Sebab one wavelength is a sine wave, right? This is only half a sine. So it's just half wavelength. Now the professor also vibrated and we saw two, just now, two segments. This is node, this is node. We saw two segments, node, node, and node. So this is 1 and this is 2. So this is the second harmonic ataupun 2 times F1, 2 times the fundamental mode. This is F1. You have two F1s here. So it's 2F1 or second harmonic. So 2F1. So back to the equation, kita tahu F1 is equal to apa tadi? V over lambda 1 equals to 1 over 2L square root T over mu. V is square root T over mu. Lambda 1 is 2L. So if I just wanted to talk about this guy, what did I want to do? So V. So for second harmonic, we can see that there is macam pattern lah in the equation. So for this is the length L, and the length L is one complete cycle, one lambda, kan? Tadi kita tengok fixed point. This is like macam ni. This is fundamental ataupun F1. And this was 1 over 2 lambda. It was the same string. The same string was used to create this shape, first fundamental mode. Then the same string L was used to create two harmonic ataupun second harmonic. And this is equal to 1 lambda. Length dia tak berubah, tapi lambda dia berubah sebab frekuensi dia dah berubah. So, from that equation, from this diagram, we know that our L is now equal to 1 lambda. So if I were to substitute into this equation, so dia akan jadi macam ni. F2 equals to V over lambda 2. In this case, our lambda is equal to, we want to substitute lambda 2 as in terms of L. So this is going to be just 1L, right? So dia nak samakan dengan fundamental mode tadi. So dia buat 2 over 2. 2 over 2 is just 1. Sama je sebenarnya. So we can just say, mana bagi korang faham ni. Sekejap. We can just say it's 1 over 1L square root of T mu. This is F2. Kenapa? Sebab kita punya L untuk 2, untuk lambda 2 is actually 1 over lambda. Kita punya L untuk F2. L kita adalah 1 lambda. Kalau untuk F1, kita punya L adalah 1 over 2 lambda. Sabar dulu saya tahu this is confusing. I know it's new and it is confusing. Give me some time to explain this to you guys. Okay, kalau soalan boleh tanya tau. Okay, so for the second harmonic, the L is equal to 1 lambda. For the first harmonic ataupun the fundamental mode, the L is equal to half lambda. Kalau kita tengok equation tadi, kalau untuk F1, kita punya equation ialah 1 over 2L. Sekarang dia nak suruh buat untuk F2. So saya tukar F2 2 over 2L. So it becomes L equals to 1 lambda lah. It's the same thing, but they want you to use this F1 equation balik. So for you to use F1 equation balik, you just substitute 2 over 2. Okay, so this is very confusing, I know. So what happens when you have 3? Kalau 3, dia akan jadi 3/2 L. Kenapa pakai ni? Sorry, saya termarah diri sendiri. F3, 3/2 L. Kalau 2, 2 kat sini. Dia nak suruh pakai equation fundamental mode. Fundamental mode punya equation apa? 1/2L F1. Okay. Kalau 2. Kalau 3. Dia nak suruh pakai balik je sebenarnya. So dia jadi senang lah. So it becomes F3, 3/2L. F2, 2/2L. Kalau F4, 4/2L. Okay. So just pakai this equation. Substitute when necessary. So general equation dia adalah ini. Fn is equal to n times F1 or equals to n/2L. F, this is T, tension ataupun force over mu, square root. So let's say you want to know what is the F5. What is F5? Fifth harmonic. So F5 is going to be equal to 5 times the fundamental mode. If you know what is the fundamental mode, let's say it's 600 Hertz, you already know what is the answer. But let's say you don't know what it is. Let's say you don't know what it is. So what you do is 5/2L. L is the length of the string. And T is the tension in your string. Mu is the mass over length. This is typically given. Sekejap, saya ada check. Ada orang soalan kot. Okay, so Aida dah faham. Okay, Aida was asking, sorry to interrupt doktor, macam mana boleh ada T dekat equation F2? Okay, so the T came from V. Remember, I showed you guys. Kalau ada orang lain yang confused juga. So the T came from this one. V is equal to T over mu square root. This one dah belajar ke? Saya rasa ni first time kita tengok kot. But this is a standard equation lah. We just use it tak payah tahu macam mana nak derive. Just remember for the velocity, the propagation, the speed in a string is V equals to square root of tension over the mass length. Mu is mass over length. This is where the T came from. Okay. So back to what I was saying. So if they ask you what is the 6 harmonics, so F6 is equal to 6 times F1. If you know what is the fundamental frequency, you just use it. If you don't know, you use this equation, 6/2L T over mu. So jadi senang lah. You just have to remember the general equation. What is another thing that is very important in this subtopic is identifying the diagram ni referring to which harmonics. Okay, so in this case, there is 0. There's nothing going on. There's no vibration. It's not part of the harmonics. When we have this one, 1I, it is called F1 or fundamental mode. We have 2 I's, mata, kan? This is what I'm saying when I'm saying I. Rupa macam tu lah. 2 I's, it means second harmonic. When I say third harmonic, it has 3 I's. Alien. Third harmonics. And sama juga, fifth harmonics, you would have 5 I's. Pandailah lukisan saya selalu buruk kan? So 5 I's. So that is your fifth harmonic. The thing that you need to remember is, what is the shape? Kalau dia kasih fundamental, boleh tak identify fundamental mode macam mana? Kalau dia kasih 6 I's, what is that? 6 harmonic. And then they will ask you, what is the frequency for 6 harmonic? You have to know how to use the equation. And remember, when we're talking about standing waves, we are talking for fixed ends. Fixed ends. Wajib tahu. So when you have fixed ends, the node must be at the fixed points. Node, node. Tengok sini. This is node. This is also node. This is node. This is also node. Tak boleh tak ada node dekat hujung sebab dia fixed. Wajib ada node. Okay, next one. So here they are re-emphasizing about the importance of having nodes, of you to remember that there is supposed to be nodes at the end. Okay, so this is where the displacement is 0. And then this is called antinode. This is called node. No. Okay, next. So this is re-emphasizing the equation again. Fn is equal to NF1. If you know what is the fundamental frequency, best lah. Sebab terus pakai N times F1. If not, you use this equation. So L is in meter, tension is in Newton meter. This is mass per length, so this is kilogram per meter. Wajib pakai SI units in this equation. Okay, so next example 10.5. A string 50 centimeter long. Story 12:30. We have half an hour to go. Sempat ke nak habis ni? Saya cuba Okay, so a string 50 centimeter long has mass per unit length equal to 20 times 10 to the minus 5 kilogram per meter. Okay, lepas tu string tu L, 50 centimeter is 0.5 meter. Kan? To what tension is asking you what is T? Should the string be stretched? Tegangkan. If its fundamental frequency, F1. For the first case, A, kedua situasi kat sini, F1 is 20 Hertz. And the second situation where F1 is 4,500 Hertz. Okay, so now we try to use the equation, okay? So F1 is 20 Hertz. We want to know what is T. So let's use the general equation. F1 equals to, no, I'm supposed to use the general equation. Fn equals to V over 2L. No, wait, it's wrong. It's N. Saya pun tak ingat sorry. N over 2L square root of T over mu. Let me see, betul tak? N over 2L, T over mu. Sorry, mu pula. Betul lah, mu. Okay, so we are talking about the fundamental frequency. So what happens? This guy becomes 1. This also becomes 1. And I just substitute whatever values that I know into the equation. So F1 is 20. N is 1. 2 times L. L is 0.5. Okay. And then we have T, which is our unknown, and then our mu is 20 times 10 to the minus 5. This is already in SI unit, so we are good. So you just punch in your calculator, and you can find what is T. Same case over here. Let me use red now. Oh, dah tersumbat dah hidung saya, please. I need just half an hour to talk. Sekejap Group this. Okay, so continuing. So now again use your general equation. Saya nak biasakan korang pakai general equation supaya korang tak confused. So Fn is equal to N over 2L square root of T over mu. Macam Siri tak? Bunyi macam Siri iPhone. Macam perasan je. Suara Siri sedap kot. Suara saya tak sedap. So N is 1. N is 1, 2 over 0.5. The L is the same. T is unknown and your mu is also the same. Yang berbeza kat sini adalah frekuensi kan. So mu is 20 times 10 to the minus 5. Sama juga. But now your F1 is 4,500 Hertz. Solve it using your calculator. Okay. Alright. Betul tak? Oh, dia buat macam ni. F is times, okay, sama je sebab dia buat macam ni. F equals to 1 over 2L square root T over mu. Dia bawa ni ke sini. Sama je. So F times 2L is equal to T over mu. And then dia hilangkan square root. So jadi F is, dia buat cara lain lah. Kita boleh buat cara kita. Sama je jawapan dia. So if you want to use this approach, you can use my approach as well. Dua-dua akan dapat jawapan yang sama. Okay, next one. A stretched string. Oh, let me double check. Betul ke dapat jawapan yang sama? I can try. If you have any questions, you can ask me, okay? Macam biasa. Let's see. Did we get the same answer? Let's do for A. So A is 20 times 2 times 0.5. Square that, you get 400 times with 20 times 10 to the minus 5. So I got 0.08 tension is 0.08 Newton. Let's see, sama tak? Sama. So, approach kita dua-dua boleh pakai. So if you want to use this approach, you can refer back to my video later on. Saya takkan explain yang ni sebab sama je sebenarnya. Cuma dia solve in parameters instead of values. Okay, a stretch spring string is 160 centimeter long. So this is going to be 1.6 meter. Linear density of 0.015 gram per centimeter. So this is actually your mu, but not in SI unit. What do? You have to convert it. So this is going to be 0.015 gram per centimeter. Convert this to your kilogram. Can someone calculate this for me? I don't know. Bukan don't know lah, malas. So I want to write down the equation. What tension in the string will result in second harmonic? Tadi first harmonic. Second harmonic of 460 hertz. Okay, so you know that F2 is equal to 460 hertz. And you know that F2 is also equal to F and F1, right? So N in this case is 2, so you can actually solve for F1. So let's do that. I don't know why, but let's just do it. Tengok dulu macam mana. So F2 is 460 divided by 2, you would get your fundamental frequency as 230 hertz. So that's your fundamental frequency. Now let's use our general equation. Oh, we should have just used our general equation. Okay, tak apa. So Fn is equal to N over 2L square root of T over mu. Ada orang dah tolong kirakan mu tak? Please, someone. Semua orang pun malas. Someone please calculate mu for me. 0.015 gram. You want to get rid of gram. 1000 gram. You want to get rid of centimeter. 1 centimeter is equal to 100 centimeter is equal to 1 meter. Okay, tolong tekan calculator. Itu je saya minta. Okay, so back to this one. If you want to solve it, okay, ada orang dah tolong kirakan. Daniel, thank you Daniel. So it's 0.0015. 0.0015 kilogram per meter. Okay, thank you so much Daniel. Okay, moving on. So I can use this general equation using the second harmonic ataupun first harmonic. Dua-dua saya tahu. So let's use the second harmonic because why not? So F2 N will become 2 over L. 2 over 2L. And then tension is something that I don't know. I'm trying to find. And mu is given 0.0015. L is also given as 1.6. So 2 times 1.6. So akan dapat something like this. F2 in this case is apa tadi? F2 in this case is 460. Now, if I wanted to use the fundamental mode, I could. So fundamental mode through 230, 1, N is 1 because fundamental mode, 2 over 1.6 square root T over 0.0015. I would get the same answer. You can trust me on this one lah. Betul, dapat jawapan yang sama kan. So this one becomes, this is become 1 over 1.6 kan. Ini 1 over 2, 1.6. So if you bring this 2 over here, it becomes 460. And this equation becomes 1 over 1.6. Sama macam equation ke atas. So sama je. So you can use the second harmonic or the first harmonic to solve it. Of course, nak senang, second harmonic je lah. Okay, moving on. I hope I'm not too fast. So this is the answer. You would get 812.54. This guy, dia solve dengan cara equation dulu baru dia substitute, which is fine. Akan dapat jawapan sama juga. Okay, now we're going to talk about standing waves in air columns. Just now, when we talked about standing waves, we were assuming they were at fixed ends. Remember? Seorang professor, seorang pakar. When we have fixed ends, we would have nodes on the end. But untuk air column, what is air column? Air column ni macam pipe getah. pipe getah lah, macam tube So you can imagine it like a pipe getah yang korang ada kat rumah tu. Dua-dua end dia kosong. Masuk kat sini, ada air. It's not fixed. It's not a wall. It's not a hand. It's not a rod. It's just air. So when it is air, you call this as open end. And open end is for air columns lah. So when you have open end, the elements of the air have complete freedom of movement. So instead of having nodes like fixed ends, both fixed ends, you would have nodes. This one, both open ends, you would have antinodes on the side. Your standing wave would have antinodes. So how does that look like? Macam ni. So kat sini yang hujung dia adalah antinode. This is node, antinode, antinode, node. Dia pelik sikit. Okay. One thing that I would like to emphasize here, if you have a fixed end, that end should have a node. If that end is open air, macam air column, you should have antinode. If you have satu terbuka, satu tertutup, let's say this is a wall and this is air, what you would get is kat hujung ni mesti antinode, kat hujung ni mesti node. This is like for a fact, memang macam tu. So this is something that you need to remember. Okay, so tube open at both ends. So previously we talked about fixed ends, and for fixed ends, the general equation was Fn n over 2L square root of T over mu. This guy is actually V, right? Okay. So now let's ignore this because now we're not talking about a string. That was V specifically for a string. Now we're talking about open air. So kita akan cakap V je lah. Okay, we're just going to say this is V. So this is the general equation untuk fixed ends. And now we're talking about open ends. So open end perbezaan dia macam mana? So for the fundamental mode, this is 1 over 2 of a wavelength. This is 1 over 4. Okay, let me remind you how a wavelength looks like. So wavelength yang complete, this is one wavelength. Kalau kita cakap pasal standing mode, this is one wavelength. One wavelength. So separuh dari ni adalah separuh wavelength. Okay, this is half. This is half a wavelength. And if we're talking about separuh lagi dari ni, we are talking about 1 over 4 wavelength. Now, what we're seeing here is separuh daripada mata. Separuh dari mata. Satu mata adalah separuh wavelength. Separuh dari mata, 1/4 dari wavelength. So, this is 1 over 4 plus 1 over 4. You would get 1 over 2 of a wavelength. Let me write this nicely. 1 over 2 wavelength. So this is your fundamental mode. So L is equal to 1 over 2 lambda 1. And then when you increase the vibration, you would get 1I. This is one wavelength, sorry, one I. This is half I. Okay, remember what? Kalau half I sama dengan 1 over 4 lambda. Kalau satu I sama dengan 1/2 lambda. Separuh mata 1/4 lambda. So 1 over 2 plus 1 over 4 plus 1 over 4, you would get 1 lambda. In this case, 2 over 2 lambda. And then your second harmonic, this is 1I, 1I, half I, half I. And again, this translates to 1 over 4 lambda, 1 over 2 lambda, 1 over 2 lambda, 1 over 4 lambda. Tambah semua, this gets 1. This is half. So you would have 3 over 2 of lambda. So L is equal to 3 over 2 lambda. So this is, back to our general equation tadi. So V equals to F lambda kan. Rearranging this equation, I write F is equal to V over lambda. So if I know my lambda is equal to 1 over 2, if I know my lambda to be 2L. In this case, this is lambda is equal to 2L. I just substitute this into my equation. V is equal to 2L. So 1. So this is the equation for fundamental mode. Then for F2, kalau F2 kat sini, I know my L is equal to 2/2. Lambda is equal to L lah basically. So F2 V is equal to, lambda is equal to L, so just L. And then for F3, for this guy, I know my lambda is equal to 2/3L. So this would become V over 3/2L. 3/2, 2/3, 3/2. Sekejap, saya confused. Lambda is 2L times, 2L/3. Okay, sorry. 2L/3. This is 2L/3. Okay, so now we look at this pattern. First, untuk fundamental mode, F1, V is 2L, V/2L. For second harmonic, we have F2 V/L ataupun 2/2L, 2V/2L. And for 3 V/2L. So we can write this in general form as Fn is equal to N V/2L. Sama je macam open ends. Sorry, sama je macam fixed ends. So the general equation for open ends is Fn equals to N/2L times V ataupun NV/2L. Sama je lah. So kenapa saya cerita pasal benda ni kalau ada sama? Sebab nanti kita akan belajar pasal open dengan close. So you have to distinguish, and also the shape is different. Sometimes they tell you, okay, can you draw the diagram for second harmonics for an open tube? Open tube maksudnya dua-dua open air. So you have to know it has to have antinode on both sides. And rupa dia kena macam ni. So this is why we have to go through it even though the equation is the same because the diagram is not the same. And antinode and node placement pun lain. Okay. So same equation for fixed and both ends. Now we're going to talk about tube closed at one end. So this is open air, this is closed. Kita boleh bayangkan macam pipe yang disambung ke dinding lah kot. Sekejap mana pergi. Okay, so imagine you have a pipe and this pipe you glue it to the wall. I don't know why you did that, but this is going to be your fixed end and this is going to be your open end. Kalau nak imagine lah. So your open end will have your antinode kat hujung and your fixed end will have node wajib. Okay, so let's take a look. So this is your open end and this is your fixed end. So you can see here you have your node here and you have your antinode here. Now remember half I is 1/4 of lambda. You only have half I. Kalau satu mata sama dengan separuh lambda. Ni separuh mata. So it is 1/4 lambda. And then you have 1 I plus 1/4 I. What is that? Kalau kita cakap in terms of 2, this is 2/2 lambda. This is 1/4 lambda. 4/4 lambda. 1/4, sorry, silap. 2/4. Separuh kan? Separuh wavelength. If this is 1/2, I can also rewrite this as 2/4 saja je sebab saya nak samakan denominator dia. This is half lambda. 1 I is half lambda, right? It is also equal to 2/4 lambda. This is 1/4 lambda. So tambah dua-dua ni dapat 3/4 lambda. This one, this is 1 lambda. Dua mata sama dengan 1 lambda. This is 1/4. So 4/4 plus 1/4 lambda, you would get 5/4. 5/4 lambda. 4/4. 1/4, get 5/4. So your L in this case is 1/4 lambda. Your L in this case is 3/4 lambda. Your L for this guy is 5/4 lambda. General equation untuk one end yang close, the other end yang open is NV4/L. Lain and where the n is 1, 3, 5. Tadi n dia adalah 1, 2, 3. This one different. This guy is special case. When the tube is closed at one end, the equation is over 4 instead of over 2. And the n punya value is 1, 3, 5, 7, 9, blah, blah, blah. Okay, recap. Recap of resonance ataupun standing wave. Okay, so resonance is the same word. It's the same meaning for standing wave. Resonance or standing wave. So summary. This is for fixed n. The equation is Fn. I need space. Sekejap. Saya tak suka tulis atas ni. Let's make this smaller. Kalau soalan boleh tanya. Sikit lagi. Oopsie. This guy boleh buang. Kita nak summary-kan. No. Oh, sorry. Saya sesama gila ni. It sounds awful. And disgusting too. So sorry about that. Okay, so Fn for fixed n. Okay, Fn is equal to n over 2L V. Okay, kalau string, kalau specifically cakap pasal string, kita akan substitute V to be T over mu square root. So boleh letak dalam equation lah, depending on the case. Sometimes they don't want you to do that. You just use this general equation. This is specifically for string. Okay, for fixed n. Sometimes, okay, most of the time string akan buat for fixed n lah kan. Kalau open air, nak string celah mana kan. So let's say you have open air. So the general equation is n over 2L times V. There's no string for open column. There's no string. String hanya untuk fixed n sahaja. And the n for this guy is 1, 2, 3. The n for this guy is 1, 2, 3 juga. Sama je. Rupa dia lain. Rupa dia kalau fixed n, hujung dia kena node. Hujung dia kena node. Dan lukislah macam mana pun. For fundamental frequency, you have 1i. For second harmonic, you have 2i. For third harmonic, you have 3i's. Satu mata, dua mata, tiga mata. Sama juga, 5 mata, 6 mata. Okay. And then for your open column, ataupun both ends are open, your equation is this guy, and the ends must be anti-node, an. Tengah-tengah kena node. So you have to imagine you need to have one eye tapi split into two, dua-dua anti-node kat ujung. Dia satu eye. Dia satu eye. Kalau tambah dua-dua ni jadi satu eye kan, tapi dia punya shape terbalik. Sama juga kat sini dua eye. Ni pun dua eye juga. The total of these guys are 2 eyes. And the total of these guys are 3 eyes. Cuma cara lukis dia lain. Okay. And then this is for open plus close. Satu close and satu lagi open. Again, open and mesti anti-node, close and mesti node. Tak boleh nak emphasize macam mana lagi dah. Saya dah cerita like 10 kali dah at this point. Open and anti-node, close and node. Jangan salah lukis, wajib macam tu. Okay, so this guy is 1 over 4 of an eye. Terbalik Sorry, 1 over 4 of lambda. Ataupun 1 over 2 mata. Dia terbalik. Dia separuh daripada yang biasa kita tengok. And then this guy is 3 over 4 lambda and then 5 over 4 lambda. General equation dia adalah n over 4L times V, where the n is 1, 3, and 5. Okay, so now I want you guys to go to your book. Dalam buku dia silap tulis Dalam buku dia silap tulis. So hopefully korang boleh betulkan sekarang so that when you revise for the exam, you won't make the mistake. So untuk page 150, correction. Okay, page 150. Please change the n to 1, 3, and 5 untuk tube closed at the reflecting end. Sekejap tulis the equation just above the SEL. Equation atas SEL question tu So there is an equation. Dia cakap Fn is equal to NV over 4L equals to NF1, where N is 1, 2, 3. Salah. It is N equals to 1, 3, 5. Orang tu tersilap buat Okay, sebab yelah, kan tersilap. Okay, so with that said, apa lagi kita boleh cover? Kita kena buat soalan sikit and then kita habis. Okay, sikit lagi. 10 minutes. Can we do this in 10 minutes? I think we can. Okay, kita buat lagi juga. So the range of a certain pipe organ is 8 Hz to 30 Hz. What range? So ni adalah range dia, frekuensi dia daripada 8 ke 30 kHz. What range of pipe? Dia tanya what is the length? Length necessary if they are open at both ends. So we are talking about an open end punya standing wave punya situation. So open end punya equation is Fn N over 2L times V. Assume that the speed of sound is 343. So we can substitute that for our V. What range is necessary? So let's try to find out. Saya pun tak tahu. So F at maybe number 1 is 8 Hertz. Okay. And then we assume this is our fundamental mode lah sebab dia paling kecil kan. Frekuensi paling kecil adalah fundamental mode. So 1 over 2L, we don't know what the L is. We try to find out what is the length that we need. And our V is 343. Okay. So using my calculator, I solve for L. L is 343 divided by 8 divided by 2. So L is 21.44. What is the unit? The unit is always in SI unit. In this case, L is length, meter lah. Okay, and then we go for the biggest frequency. I don't know what frequency that is. Kita akan assume it's just N. So Fn is 30 Hertz. I don't know what that is. I don't know what harmonic this is. So 1 N over 2L 1 over 2L times 343. Just not solve for L. Oh, we already got L. This is L. If you are assuming that that is F1. But macam mana saya nak tahu what is the harmonics? So kita boleh pakai approach ni lah. So let's see. What is the harmonics? So 30,000, N is unknown. 2 times 21.44 times 343. I will know what is the harmonic yang paling besar. So 30,000 times with 2 times with 21.44 divided by 343. So my N, wow, my N is, where should I write this? Oops. Kejap. Group. Okay, 2. Okay, so my N that I got for this is 3750. 3,750 harmonics is present in this pipe organ. So banyak lah. So banyak gila I. Kan? 3,750. So I don't know what the answer is actually. So let's see. So the length is 21.44, betul. What range of pipe length is necessary if they are open at both ends? Oh, they use this equation. So F equals to somewhere V over 2L. Oh, okay. So here they are assuming that both are fundamental frequency. That's weird. Okay lah. I would say this is straightforward. This one is kind of fishy. Kejap. Fundamental. Kenapa nak bagi dua fundamental? Okay, so the one that I showed you here, okay, Fn is equal to 30,000 n over 2L times 343, and then we figured out what was the harmonics. This question is legit, soalan ni memang boleh ada. Ini soalan yang betul. Soalan ni saya tak sure kenapa dia cakap ada dua harmonics dalam satu pipe. It shouldn't be the case because we can only have one fundamental. So kita akan abaikan dulu soalan ni. Okay. So next one, a closed organ pipe is 3 meter long. 3 meter. What is fundamental frequency produced if this is closed at one end case? So one end case general equation is n over 4L square root of P. Sorry, we don't have the string here, so it's just V. So V sama juga 343. V is 343 meter per second. At what frequencies between 20 and 20 hertz will this pipe resonate? Okay, so we want to know if we are assuming this is 20 hertz punya fundamental frequency and this is the maximum frequency. So we want to know how many harmonics dia resonate. How many harmonics it will resonate. So F1, 1 over, so kita terus kita cari N. Okay, F1 is 1 over 4L. 4L is 3, and then V is 343. So this one would give me the fundamental frequency would be 343 divided by 4 divided by 3. I would get 28.58 hertz. So this is my F1. This is my fundamental frequency. So whatever multiplication of this guy, that would be the harmonic. So let's say saya nak tahu what is the second harmonic. F2 is 2 times 28.58. This is your F2. What is your F3? 3 times 28.58. This is your F3. But we're not concerned about this guy actually. Kita nak tahu berapa banyak harmonik dari 20 ke 20,000 Hz. We want to know how many frequencies ataupun how many harmonics will be present from 20 Hz to 20 kHz. So we go for this one. F unknown 1 over 4 times 3, 343. Sorry, this is not 1. This is N. So no, charging first. Go watch the charging first. Wait. Yeah, wait. Oh boy. Yeah, sorry guys, sikit lagi, so sorry. Okay. So we want to know how many frequencies yang resonate dalam this organ pipe. Sikit lagi So the maximum would be a multiplication of this 28 lah sebenarnya. So let's not use this approach. Kita akan buat cara lain. Kita tengok berapa banyak frekuensi ada dalam ni. So 20 Hz divided by 28.58, ada berapa banyak N dalam ni? So 20,000 divided by 28.58 will give me 699.79 frequencies ataupun harmonics. Harmonics So if the fundamental frequency is this guy, this is my fundamental mode, whatever value 699 darab dengan benda Allah ni akan dapat within range 20 to 20,000 Hz. So let's see. So the fundamental mode and F1 will give me Fn, and N in this case is 699. 0.79 ni kita tak kira, kita nak kira yang complete sahaja. So 699 times with the fundamental mode, what would that be? So 699 times 28.58 would give me 119,977 Hz. So the maximum frequency, maximum harmonics is beating at 19,977 Hertz, which is just below the 20,000 Hertz frequency. So dalam closed organ pipe ni, kita recap balik dalam closed organ pipe ni, fundamental mode dia adalah 28.58. Macam mana kita tahu? Kita pakai equation ni lah. F1 1/4L. In this case, L is 3. And then the V we use as the speed of sound in air, 343. And you got your fundamental mode. Now it's asking at what frequencies, berapa banyak frekuensi yang vibrate dalam organ pipe ni. So kita tahu kita ada benda alah mata ni kan. Tapi kita nak tahu berapa banyak mata dalam organ pipe ni. Kita tak tahu berapa banyak. So dia tanya daripada range 20 ke 20,000 Hz ada berapa harmonics. So kita kira dulu, we divided by the range divided by the fundamental mode. So kita akan dapat 699 harmonics sebab kita tahu Fn is equal to NF1. So what I'm doing here is I'm taking the range and divided it by F1 to get my N. This is what I'm doing. So I got my range 20,000 over F1 28.58 to get my N. It's just this equation. And then saya akan ambil nombor bulat sahaja sebab 0.79 ni tak legit kan. So N times F1, 699 times with the fundamental mode will give you 19.977 Hertz. So the maximum frequency that this organ pipe is beating is 19.977 Hertz. And ada berapa banyak harmonics? Ada 699 harmonics. The end. Kan lagi soalan? Betul. 699 harmonics. So this is what the organ pipe will be beating. 29, then 29 times 2, 29 times 3, 28.58 times 699 maximum. Okay. BC saya tak cover lah, tak masuk exam. Okay, so that is it. Sorry, terlebih masih sikit 3 minit. I hope everyone is clear on this chapter. I know I went a little bit fast, but we have to sebab kita ada chapter 11 and 12 lagi untuk cover. If you have any questions, just ask me. If not, have a great rest of the day and take care everyone. Okay, bye-bye.
Thank you, Doctor.
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 Welcome.